I'll record. Okay, good evening, gentlemen.
Good evening.
Yeah, so today we'll carry on. I'm doing the lecture recording. So now, today is the 12th December, Friday. So the last week, we touched on topic 5, right, briefly. Then we ended up at the topic on filter. Okay, so this is quite an important topic, filter. Filter topic is one important topic that will be covered in your quiz later on, as well as in your exam. Okay, so last week we talked about filter, but basically filter is a kind of a circuit, okay, that allows certain frequency to pass through, and some frequency will be blocked. Okay, now there are three main types of filter. Okay, three main types of filter, and they are the low pass filter, high pass, and then the band pass. These are the most important. Okay, now for this filter topic, right? These are the three things that I want only. I want you to understand these three only. Okay, now band pass filter is made up of these two, cascaded together. So don't be frightened to see this word. I'll show you. The band pass filter looks something like this. Low pass is made up of two filters put back to back. Okay, low pass and then the high pass.
Band pass.
Yeah, this whole thing itself is called a band pass. It's a BPF, short form. Yeah.
Band pass versus high
Band pass filter. It's made up of these two combined. Okay, sometimes we use the word cascaded, but it means join. Cascaded. Okay, it means join together.
Put it together.
Yeah, something like stack it. Okay, so this is something that you want to cover. Now there are some theory behind this, and there are some calculations, okay, which you need you to understand. Alright, so you look at the notes, okay, under the active filter. Okay, so the last week we talked about, I think I showed you something like this, the filter response, right? Yeah, low pass, goes up. FC means it's the cutoff frequency. Yeah? Okay, so a low pass looks something like this, high pass filter looks something like this. Band stop we are not touching, so this one you can cross out. Then the band pass looks something like this. Okay, so that's quite important. Now, okay, so this is one picture. By the way, we will go on to this one first. Now, okay, so for any question about this one, so far filter part here and faster. So it's now it's okay. So if okay, right, then we can you all see by the way?
Yeah.
Is it too dark? You can see.
It's okay.
Because I scared you turn on the light a little, the thing very bright in the video.
Yeah, can see.
If you can see, then I'll just leave it as it is. Okay, so now in that case, right, let's move on. Now for the cutoff frequency is given by the FC. Okay, FC is the cutoff. So if I were to sketch for you a low pass filter, let's say start with low pass filter. Okay, you will see this signal goes down, then you cut down, roll off. Okay, sign attendance then. Thanks. So basically, what happened is this. Now this is the cutoff, right?
Yeah.
If I then call it FC. Now how they roll off? This is the. If you look at the plot, look at the waveform. This is the dB is the gain versus the frequency. So this is the dB decibel gain. This is the frequency plot. So you will notice that it's always 0 dB here. 0 dB, I'll explain to you why 0 dB. 0 dB means there is no the filter itself no gain. Filter. Okay, so it's from this 0 dB you will drop minus 3 dB down. Okay, from here 0 line you will drop minus 3 dB. Okay, you will drop by minus 3 dB, then you intercept this line, then you draw a line here. This is the cutoff frequency. Cut off. This is standard. It's a standard. Okay, minus 3 dB is a standard figure. Okay, so you can see, you can read your notes there, right? You see that it dropped by minus 3 dB. So if you were to look at your notes, here is the 0 line, 0 dB. So you will drop by minus 3 dB. So then you intercept this point and then you draw a line down. This is the cutoff frequency. Okay, that is for the low pass filter. So for the high pass also the same thing. High pass filter looks the same. So let's say if you take a look over here. Okay, they show you a simple formula here. Basically what you do is that they express the gain AV, right? dB, very similar to what you did. Yeah, like what you have done. So the gain is of this is 20 log 10, right? V out over V. Yeah. Okay, you sign your 10. Okay. So this is the thing that you can take note. Okay. Okay, the rest is the same. But if I were you, I just remember this. This is the most important. The gain in dB is 20 log V over V. Okay. That's a decibel scale. Okay, now to further on, to add on, okay, for the filters, right? We are looking at this page now. You can turn to your topic 5 on the filter part. Now there are two main types of filter. Okay, the low pass one and the high pass filter. Now some of you may know that if you use components, passive component, this component like resistor and capacitor, you can actually make a filter, very simple, look like this, right? Yeah, where you need a resistor and a capacitor in this configuration, or high pass this way. Okay, you can actually make a simple filter. Alright? Okay, now in order to find out, let's say for example I have a capacitor and a resistor, right? Like this, for the case of this case, low pass filter, LPF, short form, low pass filter. Now I can calculate what is the cutoff frequency, FC. Very simply, the formula it applies is 1 over 2 pi RC. 2 pi RC. Okay, where R is the resistor value and C is the capacitor value of this circuit. So you can work out the cutoff frequency. FC means cutoff frequency. Okay, so this is for the case of a low pass filter. Now for a high pass filter, it will be slightly different, but you're still using the two same components, C and R, but except that the thing is exchange. Exchange. So this is for the case of a high pass filter, HPF. Okay, but the good thing is this, the good thing is that the formula is the same. Okay, so that's the nice thing. Whether is it low pass or high pass, the formula is still the same. FC 1 over 2 pi R times C. R is the resistor value, C is the capacitor value. Okay, so let's give you an example. Now you can see, now maybe you should take note also. Now the second order filter you are not tested, so you can safely cross out. Yeah, you only be tested on first order filter. So this one you can easily cut it out, cancel it. Second order you will not be covered. You only be covered on things like the first order. Okay, first order filter. So for example, this is the case of a low pass filter. Now I think it's very important you must try to remember the precise configuration. Just remember one will do, because don't confuse by memorizing both. It doesn't make sense. Just remember one. If you want to remember low pass one, you just take it that I need the R here and the C here. This will be a low pass. Now what is this? Do you know? Op-amp. It's a voltage follower. That one. Okay, it's a voltage follower. So let me erase this part here. It's a voltage follower. Okay, so what you do is that now to make the filter active, right? Why do I say active? Main reason why I say active filter now.
You need a supply.
Yes, correct. Okay, active because now I use a op-amp, right? And we know that if you use op-amp, you need supply. Therefore, it's active. So for the case of the active filter, it will look something like this. Okay, whereby you use a R and a C. Yeah. This one is this is the what is this called? Unity gain, right? It's not, yeah, the feedback is unity. There's unity means what? What is unity? Unity means one, right? That means no gain. In other words, it's something like a voltage buffer. If you have
so for your topic, your active filter, you don't use any gain. For this module, you don't use any gain.
No gain. The thing that we cover, right? The question is whether the active filter, this part, right, do you have any gain, right? Of course, I can put resistor here to make, but no, we only cover unity gain for this our topic. It means that we only test you based on this very simple first order. Okay, we will not touch on the second order one. So the gain is unity. Okay, but this you must be able to identify R and C, right? Straight away I tell I know this one is a low pass. Low pass filter. Alright? Okay? So the cutoff frequency you must know, this one you must know. Now FC is 1 over 2 pi RC. This one you must remember clearly. Okay? Now I want to explain to you also why is it that we saw just now earlier the curve, right? The frequency response plot. Why is it 0? Do you know why is it 0 dB as a reference? Do you know why is it 0? Question mark. Why must start from 0? But why? Why 0?
You see, there's no gain.
Okay, now I explain to you. You know why 0? I explain to you why you must start from 0. Now explain to me what is the gain here?
0.
Gain 1, right? Okay. So why 0? Okay, very simple. Remember just now I explained to you the gain in dB. Okay. Remember this? What is the formula? 20, right? Log AV, right? Log AV, yes, correct. Because just now you told me this gain is 1, right? Because this is unity. So what is AV? 1 unity, right? Okay, what is 20 log 1? Can you press your calculator for me? 20 log 1. 0, right? So therefore this is the 0 dB. You see, this is the 0 dB because this fella got no gain, so called gain. When I say no gain, I mean there's no, the gain means 1 unity, right? Therefore 20 log 1 is 0. Therefore you can see that the plot that you always start from 0 because this fellow got unity gain. Do you understand? So it's 0, is it? Because 20 log 1 is 0. So from here then you drop by 3 dB. This is a standard, minus 3 dB. Okay, this point, right? Then you draw a line here, say it's the FC. Okay, is it very clear? Can I? This side. You consolidate for me. Okay, is it alright? So the first order, then second order is not covered, this one. So second order filter not covered. Okay. Now the filter roll off also we won't cover because ideally, right? In the ideal case, the best filter in the whole wide world doesn't exist, unfortunately. I say the best filter, what do I mean? What do you think is the best filter? How would the frequency response look like? If I say it's the ideal filter, the best, how do you think the thing look like? Any idea? What's the best filter? But it doesn't exist in this world. The best one. Yeah, the best filter in this world doesn't exist. It will be something like this. The best, right? Because it's very sharp, right? Cut off. Even the best Ferrari car in the world cannot stop immediately. When you jam the brake, it stops at the spot. Can you? No such thing. No? The thing will drag, right? Because of friction, right? It will move a bit. Okay, maybe the tolerance a bit, but still have to short. Yeah, even it's shorter, right? So the best filter in the whole wide world doesn't exist. It will look something like this. Immediate cut off. But it doesn't happen, right? In the real world, I think you will know that this thing will have a roll off. Gradually die down, right? So this one I explain here. Okay, now the higher order the filter, the sharper this thing is. Hear me? But because it's beyond doing the first order filter, the roll off, that is quite gradual. You want it to be steep, but it's not going to happen in the real world. The whole thing is impossible. Yeah, it's not possible. Unless your filter, even the best filter also won't have a direct, what I've shown you. It will gradually come down. Okay? So let's move on. So for the case of a band pass filter, let me erase this part. Okay, for the case of a band pass filter, okay, we will make use of two low pass, one low pass filter and one high pass filter, HPF, something like this. Right? If you combine these two, it will give you this thing called a band pass, BPF. Yeah, you cascade two stage, one here, one here. You combine. This is called a block diagram. I'm just showing you the block. Of course, you can draw the circuit, right? So I show you the one that something like this. Yeah. You can draw this, right? But what I show you here is in terms of the block diagram. Okay, so this is a band pass. So for the band pass filter, the response will look like this. FC.
Not high pass first.
Low pass first. The low pass frequency is higher than the cutoff frequency for low pass is higher than this one.
But if in the diagram, in the chart diagram is the high pass filter.
This one. This one is FC2. Based on not covered. And throw away. Okay.
But in the graph, you draw, the high pass first, right? Then you draw the low pass, right?
No, the low pass looks like this. Yeah. The high pass looks like this. So when you combine, you overlay. You know what I mean? This one is a combination of two. Okay, maybe a question. This is a band pass filter response. Okay, this is dB. Now for the low pass one, I use two color. We use blue here. Your high pass filter will look like this. Okay, this blue one is the high pass filter. Okay, this is the high pass. The one in blue is the high pass filter response. Your low pass one will look something like this. Okay, but when you combine these two, okay, you chop off this part. You see? And you also chop off this part. So therefore, you can see that I overlay. It looks like this. Okay, right? So it looks something like this. So this is called the bandwidth. From here to here is called the bandwidth. This one is important for your exam. This band pass filter. You will be sure one question. Yeah. Okay? Band pass. This one you must look at the notes. But I'll be recording the video. For those of you who just now came in late, I have the video recorded. We'll upload to YouTube. Okay, those those of you who came in late, you can watch. You missed out a little bit just now. Oh, okay. So this is the bandwidth. Bandwidth, what is bandwidth? Or the pass band. We call it the pass band. Pass band means is that the frequency that can pass through in this filter. Normally, this band pass filter has a certain range. Maybe I give you an example. Just say maybe if I tell you this band pass filter has a range of maybe say 470 Hz to 1 kilohertz, for example. Okay, it has a range. Okay, a range. You know what I mean? Okay, so a band pass is made up of using a low pass and a high pass cascaded together. Okay, so this is called the bandwidth, short form BW. Yeah. Yes, the FC2 minus the FC1. This is the FC2 minus the FC1 gives you the bandwidth. So the bandwidth, what is the bandwidth of this? Can somebody tell me? What's the bandwidth? 470 Hz to 1 kilohertz. What is the bandwidth? 530. How do you get 530? 1K minus 470. Then I get 530 Hz is my bandwidth. Alright? Okay, it's actually shown here. Here.
Higher frequency.
Yes, the upper frequency minus the lower cutoff frequency. FC2 minus FC1. FC2 minus FC1. Here is higher. I'm just giving you an example only. This one. Just giving you an example. This one 1K, right? I'm just giving an example. This one is something like 1 kilohertz, right? This is 470. Example, example. Is that okay? Now also Q factor. I'm going to talk about this next thing. This Q factor is a term. When you talk about filter, they always talk about Q factor. What is this Q factor? Q factor is given by this. Now, of course, you have to find what is the center frequency first. F center. Is it in your notes? Yeah. Center frequency is equal to the square root of FC1 times FC2. Okay, so the Q factor actually tells us how narrow or how wide the band pass filter is. Okay, now usually, if you want your band pass filter to be quite good, it has to be quite narrow. It cannot be too broad, because too broad means any frequency can go in, not very good. So kind of narrow, a certain range that you want only. Okay, right? So maybe give you an example. I mean, some of you listen to the radio, right? Walkie-talkie also same thing like radio. You know, like you listen to class 95, let's say. Class 95, usually if you have a good receiver, right, the bandwidth very narrow. You really want to filter only, like, let's say the class 95 megahertz, right? 95. Like you want that certain, you don't want very broad. Because you got noise coming. You know what I mean? So you want to be quite narrow in that sense. So we can calculate this thing called the Q factor. Q factor means if you know your F center, right? Because you know what is FC1, you know what is FC2, right? You can calculate what is the F center, the center frequency. So you take the center frequency divided by the bandwidth. That will give you the Q factor. Is that right? Yeah? So that's why it says here that it's quite advantage to have narrow band pass filter. Not too wide, you don't want too wide, you want just about narrow. Okay, so this is just another diagram to show you. Okay. Yeah, I think it is just some. Okay, now maybe you can take a look at some examples. Okay, okay, this is a good work example for you. Can you take a look at your notes? Okay, it says that over here the band pass filter. Okay, a band pass filter has a certain frequency, the high and the low. Okay. You see? Okay, if you look at this question, it says that the band pass filter has a frequency, cutoff frequency, two given cutoff frequency, one at 100 Hz, the other one is 1 kilohertz, respectively. That means that This one is how many? Okay, maybe use this example. Let's try to this one here. So the 100 Hz, right? 100 to 1K, right? 1K, yeah. So here is 1K lah.
Yeah.
Here is 100.
Yes.
Okay. So you are supposed to calculate all those things that's given. Sketch the response. Okay, no problem. You can sketch this one. Okay. Then what else? Calculate the Q factor. Okay, so you can calculate what is the cutoff frequency FC2 minus FC1, right? You get the bandwidth. So it's 900 Hz.
Yeah.
Okay, then you can calculate what is the Q. Right? Okay, so this is a word example. I think you have another one. Okay, of course you also can look at this, the part B. Yeah? Okay, it says that the passband gain of this bandpass filter is 10 dB, and if it's an AC signal of 1, always check out the frequency. You don't really care about amplitude. You more on the frequency. 500 Hz. If you apply to this filter, can the frequency pass through? 500 Hz can go through or not?
Yes.
Can, right? Because here is 100, 1K, so your 500, you are somewhere around here, right? Let's say around here at 500, right? 500 Hz. So can, right? Can go through, so no issue, can go through, no problem. So you can see that, yeah, the signal is within the pass band, right? So you can pass through. This is a normal question we ask also. Yeah, of course you have to calculate the gain in dB. So you take the 20 log. Use the same formula just now I explained to you. The AB gain bracket dB equals to 20 log 10 the AB. Okay. So the amplitude will remain the same. The signal amplitude will still remain the same to pass through the signal. Is that okay? Oh, why can't do this thing? This thing. Still tracking. Okay. Any questions so far? Start. Is there a sound? Oh, I got a record.